Here's a great related rate problem that requires us to make some geometry uh, connections. So we've got some cone. Imagine an ice cream cone. Imagine this being weld, and you're making an ice cream cone, and you're filling it with ice cream. Only instead of ice cream, it's water. And instead of an ice cream cone, it's just a cone-shaped tank. And so water's flowing in, and it's flowing in at a rate of 4 cubic inches per second. So imagine water is coming in at 5 inches cubed per second. It says the cone has an altitude of 4 inches and a base radius of 3 inches. So we know it's already drawn here, but this is 4 and this is 3. How fast is the water level rising when the water is 2 inches deep? So in other words, when h equals 2, how fast is the water level rising? So when h equals 2, what is dh dt? And what we know, well, we know that dv dt equals 5 inches cubed per second. It's a constant because that's the water flowing in, the volume at this given rate. So we want to find dh dt. The issue, though, is that my equation now, volume, is in terms of both radius, which is changing, and h, which is changing. So what we need to do is remember some things about similar triangles. So, if we take this and our base radius of 3 and our height of 4, well, let's say that, we're not completely full. So let's say that our height is only um, let's say here's our height, some height h, and here's some radius r. So some radius r, some height h. And what we know about similar triangles is that the ratio of h to r for every value is going to equal 4 over 3. And that's a known that we have about similar triangles. So, if we had that h over r or this, big R, big H, the ratio between H and R is always going to be 4/3. So what we can do, since we want to know about H, since H is what we're interested in, let's get rid of R. We know that, well, R equals, well, we could do some cross multiplying. 4R equals 3H. So R equals 3H over 4. From cross multiplying. And so let's take this volume and let's get rid of 3 variables and get down to just 2, volume and height. So our new equation, instead of r squared, is going to be 3 over 4 h squared times h. So we're replacing r with r in terms of h. So now if we simplify this, we get v equals um, 1/3 pi times 9/16 h squared times h is going to be h cubed. And further, we get 3 pi over 16 h cubed. That's what v equals. And the question is, how fast is the water level rising when the water is 2 inches deep? So we need to find something that relates. So now we have v and h relating. Now we need to relate dv dt and dh dt. So let's take the derivative with respect to time of both sides. And we get that dv dt, and that's a known. We know dv dt equals 3 pi over 16, that's a constant, it can go out in front, times 3h squared, power rule, and then using the chain rule, we have to take the derivative of the inside, so times dh dt, and that's what we're looking for. So we get that dh dt equals, um, well, it equals dv dt times 16, so that 16 is coming up top, all over 3 times 3, so 9 pi h squared. That's what dHdt is if we solve for dHdt. And now we fill in. So we know that dv dt is 5, and we know that our h is 2. It's 2 squared. So when we simplify that, we get that our dH dt equals 20 over 9 pi inches per second. So just talking through the process again, what we needed to do, we started off with our equation up here, but it had 3 variables. So we had to express r in terms of h, and then we got, v and h related. We simplified it. Then we differentiated with respect to time to get, so that we could get a relationship between dH dt and dV dt, and then we just plugged in what we knew. Easy. Last problem that we're going to look at, this problem is it's the same type of problem, but it looks really different. And so this requires us to use a more graphical analysis than algebraic analysis. So in all of these problems, if we look down at the bottom here, in all of these problems, we're following the same 3 things. So we state an equation that's valid at any time, which relates the quantities that are changing. We do that. Then we differentiate with respect to time to get a relationship between the rates of change, and then we substitute specific values in. So we're going to follow the same strategy for this above problem. It says the function a, whose graph, so area, changing circular region. The function a, whose graph is sketched in the figure, gives the area of a circular region after t seconds. So we know that a equals pi r squared. So now we've done this. We've finished number 1. We've stated an equation that relates a and r. So it says approximately how rapidly is the radius changing after 3 seconds. So what we want to find is dr dt at t equals 3 seconds. Well, if we employ the strategy that we've used so far, we would take this function and we differentiate with respect to time. So when we do that, we get dA dt equals pi times 2r times dr dt. Since we're looking for dr dt, we get dr dt equals dA, oops, equals dA dt over 2 pi r. Well, okay, but now we need to find, we don't have dA dt and we don't have r. What we need to use is this information at 3 seconds. Well, we have this graph. What's that going to tell us? Well, we know that at 3 seconds, if we go up, what does that tell us? At 3 seconds, we know when t equals 3, my area equals 4 pi. Do I need to know my area for this equation? No, but I do need to know the radius. So I can say that the area, plugging this in for here, I can say that 4 pi equals pi r squared, which tells me that r equals 2. Now I know that value. So now I just need to know the top. I need to know dA dt. Well, I've got a graph, area, and time. I want to find dA dt. How did we do that in the past? Well, I'm looking at 3 seconds, so I'm going to go up to 3 seconds, and I'm going to draw my trusty tangent line. It's not the most accurate method, but it's going to work. And if I choose 2 points, let's choose like this point and this point, and I think about the slope, I go over 3 and I go up 2 pi. So dA dt, using drawing a tangent line and approximating that slope, would be 2 pi over 3. So now I can fill in what I know. dA dt, 2 pi over 3, and I got that graphically, over 2 pi r, and the r I also got graphically. Things are going to cancel off. 2, 2, pi, pi, and what I'm left with is 1 over 6 if I deal with that fraction appropriately. And that is about it. That is That's the last problem that we're going to do for related rates. So we'll be working with these for the next couple days. They're fun problems. Let them be fun. They let the math really come alive. So enjoy this, and that's it.